Today I'll be talking about quantum weirdness. And I think to talk about this, I first want to go back to a paper by Einstein, Podolsky, and Rosen. That's EPR, 1935. And what Einstein argued was that quantum mechanics is incomplete. So what Einstein used in this paper was position and momentum, but we're working with discrete quantum mechanics, so we'll just use, up and down or 0 and 1. So suppose you have, so I want to give Einstein's argument. So suppose you have 0, -1. Wait. So suppose Alice and Bob share a pair of entangled particles, like this. If Alice measures in the 0, 1 basis, Bob will have the opposite particle no matter what Alice measures. So if she measures a 0, he gets a 1. And if she measures a 1, he gets a 0. And if she measures in the plus or minus basis, if Alice gets a plus, Bob will always get a minus. And if Alice gets a minus, Bob will always get a plus. So, because Alice and Bob can be reasonably far apart and can measure at the same time with relativistic speeds, Bob's particle cannot know whether Alice measured a 0 or 1 when Bob measures it. So what this says is if Bob, classically you would think that if Alice can predict what Bob gets, which she can because she could predict in the plus-minus basis if she measures in the plus-minus basis, and if she can predict in the 1-0 basis if Bob measures in the 1-0 basis. So if Alice can always predict 100% what Bob will do, then there must be something in the quantum state that tells what Bob will get when he measures it. Yes?
Should the state on top be 0, 1, -1, 0?
It should be. I'm sorry, I wrote down the wrong state. I'm going to switch to 0, 0 plus 1, 1 later in this lecture because then, I'll tell you why when I get there. But, so you would think that there's something in this quantum state that tells whether it's going to be a 0 or 1 when Bob measures it. But we know, according to quantum mechanics, that there's nothing in the state that tells whether it's going to be a 0 or 1. So what that means is that there must be a more complete theory of reality than quantum mechanics. So this is what Einstein argued. And Schrödinger wrote a paper that answered that. And Schrödinger's paper said the qubits the particles are Verschränkung, which is a German word that means crossed arms or crossed legs or intertwined fingers. And that's why this happens, which really is not that great of an explanation. And then Schrödinger, later translated Verschränkung into English as entangled, because crossed would really have not worked. So Well, nobody paid much attention to Einstein's argument for the next 25 or 30 years or so. And Einstein was never satisfied with quantum mechanics completely. But quantum mechanics worked. So they ignored this, objection to it. And then in 1964, Bell published a paper that said, well, Einstein, was both right in that there's something very strange going on here, but wrong in that there's no way to complete this theory to a real theory because the arguments of quantum mechanics contradict classical probability theory.